Welcome back to another lecture on quantum field theory and quantum entanglement. Now, we were dealing with the quantization of the electromagnetic field, and we see that it's a quite involved process essentially, okay, and it involves several steps, several subtleties, and that is one of the main reasons why we are treating it in the last thing. So, initially we could have started with the electromagnetic field, but there are several as we are seeing that we are seeing with a lot of subtleties. So, we started with the scalar field, then we started with the fermionic field which has its own subtleties, and the last one is the electromagnetic field, which we see that it has its own subtleties. So, historically the electromagnetic field was one of the first ones to be quantized essentially. Now, the point is here that what we have seen is that in the Lorentz gauge what we have been trying to follow is that okay, I'll just show you the so what we have been trying to see is that, so we were trying to quantize the electromagnetic field in the Lorentz gauge. So far we have not imposed the condition of the Lorentz gauge condition, which is del mu A nu is equal to 0. What we did was we modified the action essentially in terms by adding this term. In general we can add 1 by 2 alpha del mu A mu is equal to whole square essentially, but we chose alpha is equal to 1 and then we added this term, and this gives you this modified equation of motion is box A mu is equal to 0. Now, box A nu is equal to 0, and now this makes all the fields dynamical essentially. So, it makes all the fields dynamical. So, in fact, you have pi 0 which is not equal to 0, which is given in terms of del mu A mu, okay. And so, you have pi I which is given by del I A I 0, which comes from the F mu square term, and A I dot, okay. Now, using this we impose equal time commutation relations, and then we ended up imposing these conditions, and we proceeded in terms of the creation and elimination operators, because these equal time commutation relations are Lorentz invariant, and we can then assume that it will all work well, and then we impose this creation and do the expansion in terms of the creation and annihilation operators, and we see that putting back these expansion into these equal time commutation relations, we end up having commutation relations of this type, where there is a negative sign for the in the lambda lambda prime essentially, of which is the polarization the orthonormal relation of the polarization vectors, which comes from the orthonormal relation of the polarization vectors. Now, looking at the polarization vectors, we see that there are 4 of them. There is epsilon 0, epsilon 1, epsilon 2, epsilon 3, all of them have a space time index and also the polarization index. You remember that there are only 2 polarization vectors for the spin for the photon, but here we are dealing with 4 of them. So, one of them is time like, essentially one of them can be chosen to be the time like one, and the other 3 out of the other 3 we can choose 2 of them to be space like. The other 3 would be space like. Out of this, 2 of them could be chosen to be perpendicular to the transverse to the momentum. So, we chose epsilon 1 and epsilon 2 be transverse to the momentum, and if the momentum has the form 1 0 0 0 1, that means its unit vector along the z direction, okay, with an energy 1 essentially, okay, and then you have the epsilon 0 to be this, epsilon 1 to be this, epsilon 2 to be this, and epsilon 3 to be this. You see epsilon 3 is parallel to the direction of momentum, so it is longitudinal, and epsilon 0 is 1 0 0, it is time like essentially. So, out of this 4 we have this issue, meaning we know that they are not completely physical, because there are only 2 physical polarization vectors, okay. And so, if you check which ones of these are really creating problem, you see that the red flags raise for the time like components essentially, which is the A0 component. A0 dagger of the A0 the creation and annihilation operators corresponding to the A0 component have a negative sign, and the moment you have negative signs, you know that you have problems because the norms are negative essentially. Okay, you have norms are negative, and that means negative probability, and this all can be traced to negative kinetic term essentially. Now, how do we solve this problem essentially? That is the issue we are going ahead essentially, that there are negative norm states for A0. Okay, but this means it does not make sense because it means negative probability and so on. So, essentially all these issues which we have also seen. So, what means that we need to somehow but remember we have not so far imposed del mu A mu is equal to 0. Now, the point is that whether we should impose this condition at the operator level or whether we should impose it at the Hilbert space level. This is where the difference comes essentially. So, the idea is to impose this condition such that the negative norm states are removed essentially. Okay. The hope if one imposes so if you impose this gauge fixing condition, the negative norm states are removed, which is sort of true, but the procedure is slightly different. You do not impose this but it turns out that the procedure is slightly complicated. It is a bit okay, let me why call it is complicated essentially. We cannot it turns out this procedure is complicated because it cannot this condition cannot directly be used at the operator level. Why? Because if you impose this condition directly at the operator level, then these equal time commutation relations, if used at the operator level, the equal time commutation relations are no longer valid. Why? Because we added this term in the Lagrangian, which is half del mu whole square, del mu nu whole square, and that makes it A0 dynamical because A0 dot is not 0. So, it makes it dynamical, and that is how we got this all this meaning equal time commutation relations to work. Now, the moment you say that okay, let me if I impose it at the operator level, then this will not work. So, one needs okay, so the one needs conditions not at the operator level but so you don't we don't want meaning conditions at the operator, but at directly at Hilbert space level or otherwise essentially Fock space level. So, what we meaning so suppose if I impose this condition that only those states which satisfy these conditions are the physical states. So, that means this will remove out all. So, something like del mu E mu should acting on the state should goes to 0 essentially. Acting on the state instead of on the operator, acting on the state should go to 0. Okay. But this turns out to be okay, but then okay. So, this will remove if one imposes del mu A mu directly on states to like this, then perhaps all the negative norm states will go away. Okay. Now, the point is that again it turns out that if the state is vacuum, okay, if the state is vacuum, we will end up having problems essentially. So, we will end up having problems. Suppose if we have so let us decompose A mu field as follows. Let us decompose fields as follows, like previously we have done also in the same manner. So, the A mu field would be A mu plus of x is equal to integral d cube of p 2 pi cube 1 by root 2 p sum over lambda is equal to 0 to 3 epsilon mu lambda a p lambda e power minus I p x. So, this is the aplex. Now, this can annihilate the vacuum, but the derivative of this is not equal to 0. Derivative of A mu plus, if you take the p acting on the vacuum, that one is not equal to 0. So, that condition will not be satisfied essentially. So, that condition will not be satisfied on the vacuum. So, again essentially that means so okay, sorry, let me so let me do this by cube by cube 1 by root 2 p. I did not introduce a minus 2 p sigma lambda is equal to 0 3 epsilon mu lambda a p lambda dag e power I p x. Okay. Okay. Now, the point I wanted to make was that suppose if you take psi is equal to 0, if you say let us take psi is equal to 0, now A mu is equal to A mu plus A mu minus. Now, if you impose directly A mu acting on psi is equal to 0, imposing, the point is that if you have A mu plus, okay, A mu plus on the vacuum is equal to 0 because it annihilates the vacuum, not a problem actually. Okay. Okay. But then you have del mu A mu minus, okay, A mu minus of 0 which is not equal to 0. Okay. So, for the creation operators del mu A acting on the state, especially the vacuum, is not equal to 0. So, this condition is too strong essentially, this condition. So, the correct condition is is del mu only the annihilation vacuum, annihilation operator acting on the states should go to 0. This will pick up all the negative norm states and throw them out essentially. So, they are not physical, this will pick up. This relation is one of the famous relations in quantum field theory. This is called Gupta-Bleuler equation. This is called the Gupta-Bleuler equation essentially. So, what you are doing is, okay, just let me revise essentially that you need to impose the quantization condition, but you do not impose it on, okay. So, we saw that if we directly do in the Lorentz gauge, there are negative norm states and the negative norm states have to be thrown out somehow, okay. Now, instead of if you directly impose it on the operator level, that means at the Lagrangian level, then your equal time commutation relations are no longer valid, okay. So, your equal time commutation relations are no longer valid. Okay. So, equal time commutation relations are no longer valid. So, this is an issue essentially. So, instead of directly doing it at the operator level, we do it at the Hilbert space Fock space level. So, we impose the condition on each state, okay, on each state that it should satisfy the edge gauge condition. But that itself also is a problem, that because that means that on each state if you try to impose it, what happens if the state is vacuum state, say for example the vacuum state, the annihilation operator easily satisfies this condition, there is no problem. But if you have the creation operator, that will not satisfy this condition. So, this is what we have seen, that the creation operator, if you look at the creation operator, the derivative of this, okay, will give me P, okay, of the state essentially, which is not equal to 0 essentially. It creates a state with a definite P. So, that gives me P essentially. So, the creation operator will not it will not lead to this condition is non-zero. So, the correct condition is that only acting on every state, the derivative of the annihilation operator should go to 0 on every state, and only such states are essentially preserved essentially. And this relation is called the Gupta-Bleuler equation or the condition, which is a this will pick out the physical, this will pick out the physical Hilbert space. This condition picks out the physical Hilbert space. But so, but actually what happens is, so does it actually pick out, there is some subtlety, one more subtlety. There is one more subtlety, okay. There is one more subtlety that yes, it does throw out all the negative norm states essentially, but the physical norm states are actually the physical states are actually a linear combination of the transfer states and the longitudinal states essentially, okay. It turns out, I will not go dwell on it in a complete way essentially, but it turns out that there are a couple of subtleties actually here. So, it turns out that the physical norm states are not always positive definite, Not all the physical norm states are positive definite. Let me put it this way. Physical states are positive definite, but in turn, but actually they are semi definite. Meaning there are some states which have 0 norms. Actually what it turns out is there are several states, there are states with 0 norm which have to be identified with the vacuum, through a gauge condition essentially. Okay, this is one of the subtleties, that it is not always all the states are positive definite. No, it is not so. Not all physical states are, but actually there are some states with 0 norm. Okay. So that means there are states which have the reason comes from the Gupta-Bleuler equation. Okay. The thing is like the Gupta-Bleuler equations require something like in terms of annihilation operators, a p of the 3 minus a p of 0 acting on the state is equal to 0. So this means the physical states okay, now if we have time like photons, created by AP, okay, created by AP dagger, okay, say for example, and if we have longitudinal photons created by longitudinal photons created by AP bar 3 dagger, the Gupta-Bleuler equation tells you that you should have states. Physical states are essentially, condition is some linear combination of them should, okay, should contain combinations. Okay. So the physical states are linear combinations of time like and longitudinal photons. So you can think that okay, so the physical states will be something like, you know, some phi is equal to some linear combination Cn phi n. Okay, where phi 0 is equal to 0. Okay, phi 0 is the vacuum state. So it is a linear combination of all possible states, and so such states will be okay. Now you can show, in this case there are no negative norms states, no negative norms are possible, no exist. Okay. But what happens is there are states which are 0 norm, essentially there are states which are 0 norm, but like I said, so there are states with 0 norm, so they have to be so this is not purely a positive, okay, definite, but it is positive semi definite, essentially positive semi definite, in the sense that there are some 0 norm states which have to be identified with negative. So, negative norm is removed, which is a good thing essentially. So, we have good thing. Finally, the Hamiltonian density, okay, let us write the Hamiltonian is given by, so given by H is equal to okay, AP bar. Okay, I is equal to 1 to 3, AA dagger and AP dagger for the 0 part with a negative sign essentially. Now, it turns out, the good thing is that it turns out that the Hamiltonian is positive definite. Okay. The reason is because of purely this relation, that the Gupta-Bleuler relation which we have seen, okay, the Gupta-Bleuler relation where is here, okay. Let me put some color to this essentially. So, what does it do essentially? The Gupta-Bleuler relation ends up writing the annihilation operator on each state should be equivalent to the A0 operator acting on the state essentially, A0 acting on this, okay. The space like and the time like contributions should be equal to 0 essentially. So, the space like and time like contributions here will cancel off essentially, okay. So, the time like and the longitudinal cancellations, okay. So, this would mean that the time like sorry, I should mention this is 3, remember this is third. So, this is, okay, let me make it more explicit, this is I am myself, this is longitudinal, this is time like, okay. This is longitudinal because we have chosen the P in the direction of Z, okay, in the direction of the contribution. So, what does it do is it makes the time like contributions to cancel the longitudinal contributions. So, the Hamiltonian remains positive definite essentially. So, okay, so good, it looks finally we have quantized the electromagnetic field, we have built its Fock space essentially, okay, and on the Fock space we impose the condition, this main condition, that which is the Gupta-Bleuler condition, that del mu A mu plus or the annihilation operator, the derivative of the annihilation operator on each state vanishes. Now, this Gupta-Bleuler condition is imposed on the Fock space such that it removes out, in fact, it removes out all the negative norm states. One, it also takes out all the contributions coming from the negative norm states to the from the time like states to the Hamiltonian and equates it to the longitudinal states to the Hamiltonian, cancels them out. So, it makes the total Hamiltonian positive definite. Yes, there are some states which are equal 0 norm states, but they do not really impact because they can be shown that they can be equated to the vacuum through the gauge condition essentially. Okay. So, what is all this finally things essentially? Finally, what is all the result of all this stuff essentially? So, in the Hamiltonian there is only transverse photons contribution. So, it is the result of all this is we can work, okay. So, we can work at the end of the day, we can work with expectation values gauge invariant operators acting on physical states So, if you work with one can work with gauge invariant operator on the physical states and whose expectation values do not depend on Cn. Okay, the Cn means these coefficients essentially that you can work without worrying. If you have physical states and gauge invariant operators, you are taken care of essentially. Okay, you can work with them. Okay, let's okay, very good. So, we can work with the physical states and gauge invariant operator, and the advantages of this, and the main advantage of this formalism is that it's Lorentz invariant. Okay, good. So, we said we can work with expectation values of all these operators, and we do not have to worry about this meaning the coefficient setting, whether it is transverse, whether it is longitudinal, or whether it is transverse, or whether it is a linear combination. None of them matter. We can directly work with transverse states, and then everything is taken care of as long as it's gauge invariant, okay, and Lorentz invariant. So finally, one can derive the propagator in this case also. So, I want all of you to derive the propagator, but in Lorentz gauge essentially. So, please derive the propagator, and it can be shown, it is shown as in the same manner essentially as we have done for the scalar fields and everything, del d a nu of y time order product is equal to t power 4 p 2 pi power 4 minus I eta mu by p square plus I epsilon e power minus I p x minus y. So, this propagator is Lorentz invariant. Lorentz invariant, and it is nicer. Okay. So, this is very useful, and it is also a Feynman propagator. So, this is the Feynman propagator. Okay. So, we will use only this propagator from now on, essentially the time invariant meaning the time order product of a mu a nu in Lorentz invariant fashion, we could derive it. Okay. We will use this propagator, and now okay, and then we will see the advantages of it. Okay. So, this sort of concludes our quantization of the electromagnetic fields. I know it took a few lectures essentially because involved the subtlety is involved in this set of the quantization of the it is not just like taking meaning it is not because of the large number of degrees of freedom, associated with this, and because of the gauge degrees of freedom associated with this, it is not easy just to quantize it. It is not like quantizing 4 components of scalar fields, and no, it is not, it is much more subtle. There are a lot of subtleties we have seen along the day, but now we are now ready because we will use the Lorentz gauge. We fix the gauge and derived the Fock states and derived the quantization, we quantized the electromagnetic field, and then we also derived the propagator in this particular fashion. Okay. Now we are now ready to introduce interactions into our model essentially. So this is what we are going to do in our next lecture. We will start coupling to matter, essentially how to couple these interactions. Essentially we can start coupling to scalars, fermions, and then we will proceed to simple process in QED, and then how to derive them essentially. Okay. So let me stop here, and from the next lecture we will start looking at interactions between the various electromagnetic field and fermions, electromagnetic field and scalars, and so on. Okay. Now thank you very much. Okay. I will see you in the next lecture.